So welcome to the Picture Language Seminar. It's a new year, and we have many interesting things planned in the next few weeks. Next week, Christopher Reba, then Kaifeng Bu, Matthias Christendahl, Stefan Voss, John Embry, Emily Rial. So you see we have a real potpourri of different fields, and it should be extremely good. And today we're happy to have Renato Renner. He is the head of the Quantum Information Group at the ETH, and well known for many things he's done in the field. He'll talk about fundamental bound on time signal generation. Renato.
Thank you, Arthur, for the introduction and of course for the invitation. I'm very glad to be the first speaker of the new year. As I told Arthur yesterday in Zurich, the new year hasn't really started. People are still on skiing holidays. Skiing is still allowed in Switzerland. It's probably almost the only place where it is. And so my group is not yet back. So therefore, I think I will not have many participants from the group, but I'm sure they will be excited to hear about the other talks. And I just was glad to hear that also Matthias Christendahl will give a talk, who was also at some point a member of the team in Zurich. Okay, so to start the actual talk, I will briefly turn on the screen sharing, and then you will see, hopefully, yes, I hope you can now see my whiteboard. And as you can see there, and as Arthur announced, I will talk about fundamental bounds on time signal generation. Of course, I will explain what that means, but let me first say that this is joint work with one of my postdocs, Yuxiang Yang. He's one of the very successful postdocs. He will unfortunately leave Zurich very soon and move to Hong Kong, where he got a professorship position. Of course, that's fortunate for him, but unfortunate for me. So the goal of that work was essentially to ask whether there are fundamental bounds of this type, like Heisenberg's uncertainty is a fundamental bound, but bounds that apply somehow to time. And this is, of course, an old question, but we hope that we have some answers that go a bit beyond what was known. So just to set the stage, let me first remind you of a few things that are true for other fundamental bounds, like Heisenberg's uncertainty principle. And maybe before I now start, let me just also encourage you to ask questions at any time. I really appreciate if people actually interrupt me, because then it feels much less like just being stuck in my own room, and I feel more lively. So just please stop me whenever you think I went too fast or didn't explain something, or also if you think I'm too slow.
So Renato, maybe you should mention that if you press the space bar, then you're temporarily unmuted. And as long as you hold the space bar, you can talk.
Okay, yes. And I think people can also submit questions via chat. And I think Barbara Draschke would then notify me of that. Okay, so in the case of, for example, Heisenberg's uncertainty principle, we have that the standard deviation of, for example, a position observable and multiplied with the standard deviation of a momentum observable satisfies a well-known bound. And the important thing, of course, to notice is that this is a bound that has nothing to do with technological feasibility. It's a bound that is imposed by the structure of quantum mechanics. Let me also mention that in information theory, we usually try to express bounds in terms of information-theoretic quantities. And in the case of the Heisenberg uncertainty principle, there is an entropic version, which one may write as follows, as the entropy of, let's say, a position observable that I call X again, plus the entropy of a momentum observable P is larger than a certain constant. And of course, here it depends on how I normalize entropy, because if I take the entropy of a continuous variable like a position, this would a priori be infinity, but I could normalize it in such a way that a phase space volume of H bar just has an entropy or a uniform distribution over a phase space volume of size H bar just has entropy 0. That's just a normalization. And if I choose this normalization, then the entropic version of Heisenberg's uncertainty principle has on the right-hand side a constant which looks like this. The exact form of this constant is now not relevant. It's more relevant just the fact that we can also express things in terms of entropy. And entropy, I mean, I write here H for entropy. This is just maybe the Shannon entropy, and which is of course equivalent or a special case of the von Neumann entropy known from quantum information, can be used, or such expressions can be useful because they have what we call an operational meaning. The entropy, for example, tells us how much information I would have to transmit in order to convey a certain value. And so the more uniform a distribution is, the more information I would need to transmit to someone to communicate to this person the value, if the person only knows the distribution, but not the actual value a priori. Okay, so again, the point here is that this is, of course, independent of any technology. This is just imposed by the structure of quantum theory. Such bounds have now been used in many arguments in foundations, and to argue, for example, that we can only determine phase space or also usually space-time up to, or map out space-time up to a certain precision. But of course, if we talk about space-time rather than phase space, we would like to have bounds that, rather than involving a position, may also involve time. And one could even say that time measurements are very fundamental when we try to map out space-time, because we could in principle reduce the whole mapping to time measurements of, we could create time signals, send them out in space and to different places and measure them there, and from the time differences, we could somehow reconstruct the geometry of space-time. So therefore, it's kind of an interesting question to ask how well we can measure time, whether there are also fundamental bounds, not only on the measurement of position like this or momentum, but also on the measurement of time. Now, in order to make sure that there's no confusion between a lot of other work that has been done in this direction, let me first make a distinction between two different types of what one could call clocks or timepieces. So let me write these two types of what one could call a clock. I mean, of course, this is not the only categorization, but for our purposes, it's important to distinguish something that one could call a stopwatch from another thing which I will call a ticking clock. So a stopwatch is essentially a device. I draw this device just here as a box that as an input gets signals in time. So maybe we had an event in time where something started. So there's a signal somewhere in time. And then later comes another event where some process ended. For example, a sprinter starts here and then crosses the finishing line here. So we have these two time signals coming into the device. And the only task of the device is essentially to measure the difference between the two times and to output the number which should estimate the time that has passed between these two events. So that's what I would call a stopwatch. Now, in what I'm going to explain to you today, I'm actually thinking of another type of clock, which is more like the clock you have when you see the clock of a church. One could call it a ticking clock. This is not a standard name, but it's a name that somehow emphasizes the point that here the device somehow generates events in time. It somehow emits signals like the clock that every hour rings, or a clock that emits ticks every second, so that I know that 1 second passed. So the corresponding picture here would be that the device has no input, but it has an output, and the output essentially consists of equally in time spaced signals. So the goal would of course be that the distance between these signals, delta t, is always roughly the same. And of course, a good clock will have the property that indeed the deviation here from this ideal behavior is as small as possible. Now, just maybe to make this a bit less abstract, one could think of examples, and they don't need to be quantum mechanical. One could just think of a classical pendulum clock. And of course, a classical pendulum clock could have a mechanism so that each time the pendulum passes a certain position, it emits a tick. And now, of course, this has to involve a measurement of the pendulum position at some point. And this measurement may not be arbitrarily precise, but the clock would certainly generate the signal of this type here. Another example could be something like a clock based on light, or an optical clock. And here one may either think of the ideas that are usually presented in the context of special relativity, where one has a light signal bouncing forth and back between two mirrors, and each time it hits a mirror, we could think of emitting a tick. Or maybe if one thinks of this more quantum mechanically, one could think of again of the phase space of the light, and then there is some oscillation, and the position of the oscillator in phase space would correspond to a certain area here, and one just lets this oscillate, and each time it passes again a certain position, one emits a tick. Now the basic question that I would like to ask here is whether or not there are some fundamental limitations on how accurate these signals could be. So you see, that's really referring to the title. What are fundamental bounds on time signal generations? Because these are time signals, and we would somehow expect that they cannot be arbitrarily precise. It's not possible to have delta peaks here in time. And of course, we already know, actually from even early work done at ETH by Wolfgang Pauli, that perfect clocks cannot exist. And so, of course, now we take an information-theoretic perspective, or that's at least natural for me as an information theorist, and ask whether we can give quantitative bounds on how well such time signals can be generated. Now, if you go back briefly to Heisenberg uncertainty principle, you see that there is a trade-off. Here, we can in principle measure a position arbitrarily well, or a momentum arbitrarily well. We can just not do both at the same time. The question is here, what could be the trade-off? There must be some other quantity entering into the game, which tells us how well we can measure things. We cannot expect to find a bound just by itself without any trade-off. And what we are going to do here is to somehow relate the accuracy of these time signals that are generated by some, what I call information-theoretic property, or very general property of the generator. So I will call this ticking clock now more generally a generator. It's a time signal generator. And we would somehow like to understand whether there are certain fundamental properties of a generator that determine how accurate the time signals can be that it can emit. Before doing that, we have to make things, of course, quantitative, and I would like to briefly introduce a measure for the accuracy of time signals like this. So the first question I would like to answer is, what would be a useful measure of accuracy? And of course, there would be in principle many choices. And you have already seen in the Heisenberg uncertainty principle case that also for position, we could measure it with, for example, standard deviation or entropy. And at the end, and we will see here that there is essentially some nice bound that we get that is true for a particular type of measure. And this measure that I will introduce could be understood as follows, and that's not, of course, something new. If I had two signal generators of the same type, and I would just let them run, they would emit ticks. Then if I compare them, they would probably emit ticks almost always at the same time. But as time passes, they will become more inaccurate. And maybe it will at some point happen that one device is one tick ahead. So maybe one device has already emitted the 1000th tick, and the other one still only the 999th. And then it could even happen that the first one already emits the 1001st one, and the other one has only emitted the 999. So this would mean that one has become faster by at least one tick. So this is somehow a dimensionless quantity, which tells us how many ticks can the device emit until its inaccuracy in time is as large as the distance between one tick. Or how long does it take until two clocks of the same type are off by one tick? And because we are just counting ticks, that's a dimensionless quantity, which is quite useful in our context. So what does this quantity mean? I could also express it in terms of standard deviation and so on. So let's look at such a train of ticks. So we could have here the time axis, could be a starting point here where the whole time signal generation starts, and maybe there's a tick at some point, and then there's another time signal a bit later, and so on, and one again later, and so on. Now, if we, for the moment, just for simplicity, assume that we could somehow build a device which only emits one tick, and that would be sufficient because we could then always restart the device whenever a tick was emitted and then wait until it emits the second tick and so on. And in that case, the ticks would be somehow always generated in the same way and statistically independent. I could now denote the time between the starting point and the first tick by t1, and the time it takes between the first tick and the second tick by t2, and so on. And then we could ask what somehow the time distribution, or I call this delta t1, delta t2, delta t3, and then I could ask myself what is actually the time at which, let's say, the nth tick is emitted. And of course, the emission time of the nth tick would just be the time it took until the first was emitted, and so on. The second until delta n, tn, so that's the last distance between the ticks. And if the ticks are generated independently, these are just independent random variables. So I could therefore say that the standard deviation in the emission of the nth tick, and we call it sigma tn, is just follows the usual law of how the standard deviation grows if I add independent variables, which would mean that the square or the variance of it would just be n times the variance of one single tick. So that would be one of the delta t's. So let me, by the way, introduce here or abbreviate this by sigma. So sigma would just be the variance of one single tick. So it would be defined as follows. If mu is the average time that passes between two ticks, so it would be the average of delta ti. It's just on average, how long does it take from one tick to the other? Then the standard deviation would, of course, be just the deviation from this average, or from the time it takes from the average time squared, and the average of that. And we could now say that the deviation of the nth tick, so sigma Tn, is therefore just square root of n times the sigma that I defined here, which is the sigma of one single tick. So why do I do that? Now it's very easy to see what this measure of accuracy could be that I introduced before. So what would be the n, the number of ticks, when I should expect that the deviation is as large that the two clocks go off by one tick. This will be the case as soon as sigma Tn, the standard deviation, is larger than the average distance between two ticks. So if this condition here holds, then the clocks will be off by one tick. So the question is essentially, what is n such that this holds? And of course, that's a very simple calculation to do. And you just see from
Renato, we don't see what you're writing anymore.
Oh, that's strange. Okay, how to where did you see it still?
Sigma Tn equals square root of n sigma is the last thing we see.
Okay, let me briefly pause the sharing and then restart it. Do you now see it again or not?
No.
Okay, then let me briefly stop the sharing. And now I start the sharing from scratch. Is it now visible?
No.
No? That's very strange because it appears here on my screen.
We just see that you've started screen sharing, but we don't see your screen.
Oh, okay. Yeah, I really don't know what this is, because on my side it shows everything perfectly. I see also
it seems to have frozen when you went to the next page.
Okay. So if I stop the screen sharing like now, then it stops also on your side.
Yes.
Correct.
Okay. That's very strange. Okay, I'll just try to start it again.
Is it possible to save the document you had and then reopen the program from where you left off?
Yes, I could do that. Let me try that. Okay, now I reopened the program. Did anything change your side?
No.
No.
So maybe I could just briefly log out from the Zoom session and log in again. Maybe that helps. I mean, I don't know else what to do because the device works on my side. So I'll just briefly log out and log in again.
Okay.
Okay, now I'm back in. So let me try again to share the screen. Do you now see something?
Yes.
Okay, good. Okay, then I'll just continue where I stopped. So, I think I somehow just did this or tried to explain that, of course, this condition that I just wrote down is now equivalent to say that n sigma square is larger than mu squared. And so you see that if I now define R, a new thing R, as mu squared over sigma squared, this is really then the bound from which on, if n gets larger than R, I would expect that the clock is off by one tick. So in other words, if I take mu squared by sigma squared as a dimensionless measure for accuracy, this has this interpretation that I just explained before. Okay. Now we have a measure for accuracy. The question is now, are there any fundamental bounds, as I said before, on this measure? And before I state the bounds, as I said, we now somehow need to characterize the device. So we will have a generator, and the question is, how useful is a generator to generate time signals? And the idea, essentially, or what turns out to be the relevant thing, which is probably not a surprise, is something that we can call the controllable dimension. D-control. So the controllable dimension, informally, and I will just give a more mathematical definition, but informally corresponds to the number of distinguishable states that the device, let's call it S, admits during its, of course it's a finite, so I assume it's a finite device. We are talking here about actual devices like clocks, and these devices have a finite accessible phase space. So of course they may be infinitely large in principle, but the number of degrees of freedom that we can control, for example, if I have a clock, I can somehow control where it starts, what the point, what the hand position is of the clock. This size is somehow finite, and I'll just define the D-control as the number of different states it can admit here. So what does this mean more mathematically speaking? I could express it, and here I need now an information-theoretic expression as follows. D-control could be defined as the maximum of 2 to the mutual information between S, or a reference system, and S. So what does this mean? So that's a typical construction that is quite common in information theory in order to measure how useful or how what's the information capacity of a device. The idea is as follows. One thinks of a kind of reference system, and this reference system is, you can think of it just as a classical random variable, which can take as many different discrete values as you like. And now you try to build a state, or to think of a joint state of the system you're interested in, of S, and the reference system, and I call this state rho S ref. So that's a joint state that includes the state of the system and the state of the reference. And I try to come up with a state which contains as much correlation as possible between this classical value here and the system here. Now I could maximize over all such states here. So let me put this here also in blue. So one may think of this state somehow, if you want to think continuously, as the integral over all possible states that the system admits, and then I take a tensor product with t, which would just be the value of the reference system. So you could think of the reference system stores somehow the perfect time t or some parameter, and this parameter is correlated to the position here. So a concrete example would be if this was just a pendulum clock, then each position of the pendulum of this clock could be mapped to a value of this reference system. And I now try to come up with a state where the position of the pendulum is as much correlated to the value of this reference system as possible. And then I maximize the so-called mutual information, which is a measure for this correlation. And for those who are not familiar with the mutual information, let me briefly define this measure. The mutual information between two systems, like a reference system and S, is just defined as the entropy of the system, if I just take the marginal state of the system, minus the entropy of the system if I condition on the value that is in the reference system. So it's somehow the difference on how much I know about the state of the system. Once, if I don't look at the reference, I have no idea what this content of the reference system is, and then I look how much I know about the system, how uncertain I am if I knew the value of ref, and that's defined to be that's what information theorists call the mutual information. And it's maybe not completely obvious, but this is really a correct formalization of the idea that D control is essentially the number of distinguishable states. More precisely, one can show that if you could really associate to the system a certain number of states, then this would upper bound this value. But you could also...
Renato, your screen is frozen again.
It's again frozen. Oh, that's a bit annoying. So maybe it happens each time I go to a new page. So maybe what I could do is just I create many new pages, and now I'll do the same trick and log out and log in again, and then hopefully we'll be fine for the rest of the talk. So let me briefly do that. Okay, so let me try again to share then. Okay, can you now see it? Okay, good.
Yes, it's
Okay, I don't know how much you saw before of it, but what I essentially did as a last thing is just to define the mutual information as a difference between entropies, which in information theory are interpreted as uncertainties. Okay, now we have essentially defined two things. The first thing I did is to define a measure for accuracy of signals in time, which essentially measures how long it takes until a clock is off by one tick. And the other thing I did is somehow to give you a measure called the controllable dimension, which captures how many different states or how many different things I could store in a system, or between how many values a system could distinguish in principle. So this is somehow a measure of the maximum information content that a system can have. Now
I just have one question. Can you say again with your example about the pendulum clock, which one was S, like the phase space of the pendulum was S and the reference system was what? Or did I get it mixed up?
Yeah, yes, okay, thanks for the question. So let's maybe look at the pendulum system for a moment. So so now, of course, I want to think quantum mechanically for a moment. I started this whole thing with just classical examples, but let's now think of, I mean, because of course, classically, a pendulum has probably infinitely many possible positions that I could distinguish. So in order to get a kind of non-trivial bound, I treat the pendulum as a quantum system. Now in a quantum system, what I would do, let's maybe start, maybe I'll just explain it in terms of this thing first, and then I can switch to the more formal definition here. So in the case of a pendulum, I would say, okay, let me just draw a pendulum. We could very roughly, and this is now a very rough estimate just to give you a feeling for the proportions. We could say that there is a certain interval in space through which the pendulum travels. This is just essentially the amplitude. And maybe let's just say if the pendulum has somehow a length L, then this X is of the same order of magnitude as L. Then if this is, if we consider this as a mass with, let's say, let's just measure the mass in terms of number of atoms, just very roughly speaking. Then we could say that what the Heisenberg uncertainty principle tells us in this case is that we can roughly estimate the position up to a precision that is proportional to, let's say, 1 over square root of n. So that's how accurately I could measure the position of this pendulum without disturbing its motion too far and too hard. Of course, if I would measure the position too accurately, I would completely disturb the momentum. So I would somehow distribute the things between position and momentum. So that would be roughly how well I could measure its position. That would certainly be true if it was modeled as a Gaussian state. And then we could say, okay, in this case, now according to the trivial intuitive definition, the number of distinguishable states is proportional somehow to x divided by delta x, which would of course be now something like L times square root of n. Now that's just an estimate of what this, that's not yet a controllable dimension, but now if I want to really go back to this more formal definition of the controllable dimension, one should think of it as follows. Think of the pendulum can of course have different positions like this or this or this one. These are just different states of the pendulum. Now what I would do is to draw here the reference system, and the reference system also can have different values in it. The reference system is just a system that carries a value. And let's say here it carries the value 1, here 2, here 3. And I'll just set up the joint state of the reference system and the pendulum in such a way that if the pendulum is in this position, then the reference system carries number 1. If the pendulum is in this position, 2, and so on. So this is essentially a description of a joint state between the reference system and the system S itself. So you can imagine that, the state would be essentially described as the state which consists of a just convex combination of the state where the pendulum is here and the reference system has 1 and all these other things. And that gives a correlated state. Now, this was just an example of how I could build that state, but I can now show that if one maximizes over all possible such correlated states, I would essentially get the same expression like here, up to certain proportionality factors. So I'm not sure this answers your question, but it should somehow illustrate how I would come up with this controllable dimension.
Thank you. Yes.
Okay. Now, by the way, it's maybe just useful, as I'm anyway talking about the pendulum, to make a small remark. Of course, in the pendulum case, in the classic or even quantum pendulum case, the frequency is of course proportional to 1 over the length of the pendulum. And I could therefore actually express the length L. Okay, let me first just write this. Now I could express the length L in terms of the frequency, which allows me now, using this expression that I just wrote down here. So here I wrote down the expression L square root of n, and that's essentially the controllable dimension. And I could therefore say that the controllable dimension of a pendulum, of just a normal massive pendulum, is of the order square root of n. And now I replace L by G over the frequency squared. So the controllable dimension of a pendulum, not surprisingly, grows with how many atoms the pendulum consists of. A larger pendulum has kind of more information that I can store in it. But it also somehow, because of this relation between length and frequency, depends on the frequency. So to actually have a pendulum with more information storage, I should have one with a low frequency. The reason is simply that such a pendulum is longer, and therefore I have more possible positions in space. But this somehow means, for the purpose of increasing the controllable dimension, it's good to have a low frequency pendulum. Okay, now it's probably time to give you a result. Now I talked a lot about definitions. Or okay, still one remark before stating a result. I could also think of an optical clock with n photons, and there a similar consideration would show that the controllable dimension is of the order of square root of n for classical light. This is just because I can determine the position or the phase of light up to a precision of 1 over square root of n, roughly, if n is the number of photons. And if I use squeezed light, then I can make the controllable dimension n. So this would be for squeezed light. So in some way one could say a device that allows me to arbitrarily squeeze light has a higher so-called controllable dimension and could store more distinguishable states in this device. Okay, now I'll tell you, first of all, just the statement. So we have now introduced many definitions, and you may now wonder, why did I do all that, and why is this useful? What interesting statements can we make? Now, the statement is now very simple to state. The statement says that whatever device I have, the accuracy of the time signals that it can emit, which is captured by this quantity R, is always bounded by some constant. So you see again the 2PE appearing times, and this is now the important part, the controllable dimension squared. So that's now a bound that one, I mean, I made at the beginning these remarks about Heisenberg uncertainty and so on. That's a bound that holds if you had no other technological difficulties to solve, if the structure of quantum theory was the only thing that limits us, then we could say, still there is a bound. Even if there were no technological obstacles, we cannot generate arbitrarily accurate time signals. The time signals that can generate with a device, with a generator, is always, the accuracy is always limited by this so-called controllable dimension of the generator. And of course, we could now apply this bound to pendulum clocks and get concrete values for what this would be. Actually, that's not hard to do. Or let me do it for the case of an optical clock. If you take an optical clock, then of course this controllable dimension, as you saw, is of the order of square root of n. This is probably a bit unrealistic with today's technology, so we are rather here. And so because the controllable dimension here appears in square, the statement would be that for an optical clock, the maximal accuracy of a time signal that I can generate is proportional to the number of photons that I have in the laser pulse or whatever that this clock that is used in this clock. And this is probably with today's lasers of the order of 10 to the 18. So we have somehow a bound on the accuracy. So we cannot, with a laser, for example, with pulses of 10 to the 18 photons, hope to generate time signals which are more accurate than that. And
Renato, I'm afraid for me it's frozen again. Is that true for others?
Yes, it's frozen.
So since when? Or is the theorem still visible?
The theorem is visible, yes.
Nothing after the theorem.
It somehow, okay, I didn't write anything after the theorem, but you don't see scrolling. Okay, so I'm not sure. I gave lectures and courses all over the semester, and this never happened. But then probably again, the only option is that I briefly log out and log in again. Then let's hope. Okay, now I'm again here, and I'll share again. I get used to that procedure, I think. Can you see it now? Okay, I hope I can now come to the end with all that, because now I actually wanted to show you some ideas about the proof, or maybe discuss the result. But before I do that, I should also add something, namely that conversely, the bound is in principle achievable. So this means that we can design very particular systems. So if you give me a system with a certain controllable dimension, then I would have the freedom to choose its Hamiltonian arbitrarily. Of course, that would be hard, but now we are talking or thinking about quantum technology, where, for example, a quantum computer is a device where I can, in principle, program it in an arbitrary way. I can essentially determine its time evolution as I want. And if I had such a freely programmable device with a controllable dimension d, then what this converse result tells me is that I could indeed achieve that accuracy if I had no other inaccuracies, of course. So that's again just a fundamental bound. This is a bit like saying that in the Heisenberg case, in principle, we could also reach that limit. It's not only a bound, it's also something that we can approximately reach. And the same is true for this particular bound. So we could, in principle, create clocks that have a very high accuracy, provided we can make this controllable dimension very high. Okay, I will only show a few ideas about the proof and refer to the paper for the full proof, because I see that time is progressing fast, but I still wanted to give you some ideas about the proof, because I think it's quite interesting to see how the proof uses information-theoretic concepts here. And for that, I first need to make a remark about this mutual information, which has a very nice property, which is called the data processing inequality. I'm not sure whether you have heard of that, but that's one of the fundamental inequalities in quantum information theory. And the inequality says the following. Let's suppose I have two systems. Let's now abstractly just think of them as A and B, and they could be arbitrarily correlated. Now the correlation, as I said before, can be measured in terms of the mutual information, which again to remind you is just the entropy of A minus the entropy of A given B, or equivalently the entropy of B minus the entropy of B given A. So that's actually symmetric. And now let's suppose we somehow process these systems. So the systems are just somehow undergoing an evolution, which has, however, the property that they are separate. So there's like a wall in between the two. So this orange line should just indicate the two systems are not communicating. They're just independently evolving according to some time evolution. And this could be an open systems time evolution. So it doesn't have to be unitary. And I end up with a system which I call A prime. So it's this, could think of the same system as A just after the time evolution, but you may also think just of a part of the system. Now the data processing inequality just tells you that the correlations can never increase, which is very intuitive, but actually to prove these things is sometimes not as easy as it seems. In this particular case, it was actually a very hard result to get in the early times of quantum information. But the inequality says at the end that if you measure correlation in terms of mutual information, then if systems don't talk to each other but just evolve, then the mutual information cannot increase. So it will be smaller, but certainly not larger than initially. And that is somehow one of the basic ingredients to the proof. Okay, now how does this proof work? And as I said, I'll just give you maybe a sketch of the proof. The idea is again to consider the system, and let's think of the system now as something like a clock, of course. As before, it could be a pendulum clock. But this system, of course, the state of the system will evolve over time. So I just indicate this here, like this could be the hand of the clock. And I first start doing the same thing as before for the definition of the controllable dimension. I just introduce another system, which I call the reference system, and I'll just set up this joint state.
You're frozen again, Renato. I'm sorry.
I'm again frozen. Okay, that's really bad. So now I'll try to do my trick for a last time, and then if it happens again, I'll just finish with the talk. So let me then leave briefly. Okay, I hope it's visible again.
Now we see it.
Yes. So again, we set up the thing like for the definition of the controllable dimension. So we somehow think of this reference system, which has a variable in it, and then we somehow correlate it to the state of the clock, of the signal generator in a particular way that maximizes the mutual information, so that this mutual information corresponds to the controllable dimension. So in other words, if I now define this to be the state rho of S, the joint state of the signal generator and the reference, I just set this state up in such a way that the mutual information between S and the reference is essentially log of the controllable dimension. So remember, this was how the controllable dimension was defined as 2 to the I. So I can also write it in terms of the log, and the logarithm is with respect to the base is 2. Now the idea is that we just let now this clock evolve and emit the signals. So the emission of a signal is just a process, like a process from here to here. It's some evolution which has nothing to do with the reference. So we now let let the clock emit, or the signal generator emit these ticks. And after that process, we have on the left-hand side somehow ticks of different at different places. So depending on what the state of the clock was, the ticks will have different times. And on the other side, we still have the state of the reference. So now the only difference between the picture before was that we now have a correlation between the output of the clock, namely the time signals, and so this is kind of the ticks, if you like, and the reference. And we could now ask ourselves, what's the mutual information between these ticks and the reference? And by the data processing inequality, this has to be smaller than the mutual information between the clock, the signal generator S, and the reference. And as we said before, by definition, this is smaller than log of D control.
So Renato, you're frozen again, but maybe
I'm frozen again. Okay.
Maybe you should just tell us.
Yes, now I'll just tell you how it continues without. So what can you see now? You can see what. Can you see this last formula for mutual information that I wrote down?
Yeah, the data processing inequality is visible.
Okay, only that. Okay. Anyway, yes, I think I cannot, maybe I'll just explain then the rest of it in words without writing something. So I hope you still remember the kind of statement, the main statement I made. And the main statement I made was that the controllable dimension is a bound on the maximum accuracy of a clock. Now, what I try to do, and not very successfully now because of these technological difficulties, is to essentially try to give you proof of the bound. But maybe the main message is that the proof really uses theorems from quantum information theory, which in particular the data processing inequality. And that's how we can really make this whole thing quantitative. So the data processing inequality is, by the way, really the backbone of many proofs in quantum information theory, from capacity theorems and other fundamental bounds. One could even use it actually to derive or to get extensions of the Heisenberg uncertainty relation. But what do we learn from this theorem? Maybe I'll just finish with that. So it would still be useful if you kind of keep now in mind the main formula I gave you, which is R is smaller or equal to the controllable dimension squared. Now I told you that the controllable dimension for a conventional pendulum actually grows linearly with the number of atoms I have in the pendulum, or like the square root of it, or for an optical clock it grows linearly in n. And this means that if you want to increase the accuracy, we have to build larger and larger systems. So of course, for example, if I double the mass of a pendulum, I could essentially double the accuracy. But this is not very efficient because doubling the mass is quite expensive. And so one could ask oneself whether there are systems where the controllable dimension scales more favorably in terms of their size. And I mean, the intuition is that the systems we considered so far, and that we are usually considering for clocks, like, for example, a pendulum or so, are systems with a collective degree of freedom. So it's just the center of mass, but we are not using the fact that the individual atoms of the pendulum could be somehow arranged in different ways. That's not a degree of freedom that we are using. We're only using the center of mass degree of freedom. Now, however, if you look at modern devices or modern technological capabilities, and now I'm returning again to quantum computing, there we are in a very different situation. If I have a quantum computer consisting of n qubits, then the number of different states I can store in this computer grows exponentially in n. It's essentially 2 to the n. So in contrast to a pendulum, to a classical pendulum, where the controllable dimension just grows essentially linearly in n in the number of atoms, the controllable dimension of a quantum computer grows essentially exponentially in n. And a simple back of the envelope calculation shows that if, for example, I had a quantum computer with, let's say, 32 qubits, then the controllable dimension would, of course, be 2 to the 32, and therefore the accuracy, which is the square of that, would be up to 2 to the 64, which is already larger than 10 to the 18, which was essentially what I told you what we can reach with a pendulum clock or with an optical clock. So in other words, a 32-qubit quantum computer could in principle reach the same accuracy as a rather big optical clock. But now it becomes interesting because if you now scale the thing up, if you now, instead of 32 qubits, take, let's say, just 40 qubits, then the accuracy will again be 2 to the 8 times higher than before. So we would have a very favorable scaling. So in other words, if we, for example, had a 64-qubit quantum computer, we would in principle get a clock which is just enormously much more accurate than any clock we had before. This is, of course, only true if you have no other inaccuracies. So this is just a fundamental bound. If you only were limited by the structure of quantum mechanics and no technological limitations. This is nevertheless interesting because for such devices like quantum computers, we know in principle that using fault-tolerant techniques, we can bring them exponentially close to a perfect behavior. So the conclusion of this whole, let's say, work, and this is that as we now understand that the accuracy of time signals that we can generate is very closely related to this so-called controllable dimension, a goal could be to build devices with a high controllable dimension. And this could be achieved essentially with the same technology that we are using to build quantum computers. And this gives somehow a new route towards interesting quantum technology. So instead of just thinking of computing devices, we could think of fault tolerance techniques and so on that are used in computing just to build much more accurate clocks that have this exponential scaling in the size, or that where the accuracy scales exponentially. So that's essentially now the conclusion in words without any slides. And I think it's maybe a good time to stop here.
Well, thank you very much, Renato. This was a really interesting and intriguing talk. And I have a number of questions, but maybe other people do also.
Yes, thank you. And I'm really sorry for these technological difficulties.
Well, I hope that
I will have to find out the source, because I will have to again give lectures in spring. And if this happens, I will be quite screwed.
When you send us the slides, then we'll put all the slides on the website.
Okay, perfect, yes.
So I have a question. If you apply your theory to one of these standard atomic clocks, that appear to be highly accurate, does it give anything of interest?
Pardon? I didn't understand the last sentence you said. There was some.
So is the bound interesting if you analyze atomic clocks, cesium clocks?
Yes. So actually, if we apply the bound, for example, for just to, let's say, atomic clocks as they exist now, we get bounds of the order of 10 to the 18 for the accuracy. Now, as I said, this is of course a bound that only tells us what would be the limitations if we were only constrained by the structure of quantum theory. Now, of course, what people who build atomic clocks fight with is not this ultimate limit, it's rather the disturbances you have from environmental influences. This is why I think the bound applies in a sense as an ultimate bound, but it's not a bound that is currently relevant because we are much more limited by technological difficulties. It's maybe a bit similar if you would say, let's say if you analyze maybe older measurement technologies to measure position and momentum, they would be far away from the Heisenberg limit. Now, of course, we are getting closer to the limit. And I think in the atomic clock, let's say domain, we are still quite far away from this limit, maybe by several orders of magnitude. Someone should really understand this in a way as a bound that is becoming relevant once we have resolved the problem of disturbances, which will of course never be perfectly resolved. But as I said, in quantum computing, there are some interesting techniques to actually decouple a system from disturbances, or at least to decouple certain degrees of freedom very nicely from the disturbances. And then this bound may become relevant. Does this answer your question, Jürgen?
You're muted, Jürgen.
For the time being, yes.
Okay.
So Renato, at the start of your talk in the classical uncertainty principle, you mentioned the entropy of position and the entropy of the Fourier transform.
Yes.
There's some inequality like that in the time case that you can identify some quantity that with a dual quantity that gives an uncertainty principle.
Yes, right, yes. Yeah, there are these time energy uncertainty relations and so on. And there is as you probably know, a big debate still ongoing of whether they are relevant or not. Actually, one of the reasons why we took the approach we are taking here in my talk is exactly that we wanted to have results which are more based on quantities that would really be directly measurable, rather than things that are kind of appearing formally. And you see, this accuracy measure R is something that you would actually very naturally use to characterize the accuracy of clocks. And also the controllable dimension is something that is in some sense directly measurable. But I cannot tell whether these, let's say, energy time uncertainty relations, what they would really mean operationally or in terms of measurable quantities. because there are examples in where people are claiming that one can essentially circumvent them, and then there are others who say, they were wrongly interpreted and so on. I'm not very familiar with this debate, but essentially my point is we wanted to evade this debate by just introducing quantities which don't have this problem of being debatable, which are just in principle, you could go to an experiment and measure them.
So maybe I should ask Cheng-Wei if you've looked at such inequalities in quantum Fourier analysis. Or maybe
Maybe here.
I don't know if he's there. It's late.
Yes, but I mean, I'm sure one, as mathematical statements, one can certainly come up with these theorems very much analogously to position and momentum.
So there should be a non-commuted form of the data processing inequality.
A non-commutative form of it.
Yes.
Yes. I mean, there are currently many extensions. So this data processing inequality has recently gotten a lot of attention again. And actually, I was also working a bit on that. And I just saw before that Marius Junge was also among the audience. And we have some work on that as well, where one can give now more precise characterizations. Although I don't have maybe something I would immediately call a non-commutative version. It would be interesting to see what that could mean precisely.
Yeah. Well, Marius has left.
Yeah, he was just here just before, but now we lost him. Anyway, he was actually contributing also a lot to this field of strengthening data processing inequalities.
Yeah. Well, I see there are many experts. Some expert have a question.
Okay, I'm not sure whether anyone has a question, but maybe it was maybe as you said, I will send you the slides, and then those who are interested can then maybe try to reconstruct what I said, having the slides and listening to the talk again. But there's also an arXiv paper out. I think the arXiv link is on the announcement that was sent out.
Yes, and you also put it at the beginning of the talk.
Oh yes, it's still visible in probably in the back of you.
Well, thank you very much, Renato. This was really interesting talk. It seems to.
Thanks again for the invitation, and thanks for all those who made it so early in the year already to a talk. That was very nice. That I was fearing that I have no audience, because if I would give the talk here at ETH, no one would appear, except maybe from Jürgen and Klaus, who are always present.
So next week, Christopher Riba, he's a postdoctoral fellow at UC Berkeley, had been a student at MIT. He has some interesting results with he'll talk about. And so we look forward to seeing you then, and to many good talks this year. So thanks again, and bye-bye.
Thank you again.
All the best.
Thank you.
Thank you.
It's a pleasure.